Welcome to the lecture on Chapter 6, which is all about concentration. And what that means is we want to express the part of something as it relates to the whole of something. So, for example, the amount of solute in an entire solution. And we'll give more examples of that. But concentration. And the reason concentration can be a little bit confusing, and there's so many different variations of these types of calculations, is that concentration can be expressed in many different ways. So, for example, in this lecture, we'll emphasize and go through problems that use concentration expressed as a percent strength. Then we will also go through some examples where the same concentration can be expressed as a ratio strength. And then lastly, there are other, not as common, but other ways of doing it, such as parts per million. So these three examples are simply still ways of expressing concentration. That is the amount of a thing, such as a solute, that is present in a whole, such as a solution. So with that, let's kind of start with this percent strength. And this is extremely important in pharmacy and medicine because most of our drugs are expressed in the delivery vehicle, however we're administering those drugs, as some sort of weight. And as sort of a weight, if it's combined with any other sort of product that is dissolved in solution or in a liquid or mixed in a vehicle base like an ointment or a cream, then you express the amount of drug as a percent. So let's start at the top, and I've tried to color and confuse because we can also have concentrations expressed when solids are mixed in solids, or solids can be mixed in liquids, or liquids can be mixed in liquids. And that's what makes some of this percent strength confusing because there are lots of different scenarios. So let's start at the top. And I've tried to color my text blue when I'm talking about liquids and kind of orange when I'm talking about solids. So the first percent strength to discuss is percent weight per volume. And when we are talking about or giving a concentration as a percent weight per volume, what has happened is we've taken some weight of drug and either dissolved it or dispersed it, the difference between a solution and a suspension. Regardless, we've taken that amount of solid and dispersed it into some final volume of liquid. Okay, so there's a concentration. There's a certain amount of the solid per a certain amount of the liquid. So the way we would express that is when we do a percent weight per volume concentration, we standardize things. So to give it as a percent weight per volume, remember a percent means an amount of something per 100. And since in this case, the weight per volume means the weight of the drug has been dispersed into some volume, the percent means per 100 milliliters. The units of volume are in milliliters. Okay, and since it's a percent, it's per 100 milliliters. And again, the other way we've standardized it, whenever you see weight in a percent weight per volume, the weight will be in grams. So whatever the number is, the units of a percent weight per volume will be that number in grams per 100 mils. So if I tell you something is 16% weight per volume, then you can say that thing is 16 grams per 100 milliliters. If something is 60% weight per volume, that means there are 60 grams per 100 milliliters. Okay, that should be hopefully clear. Now, a variation on that would be, instead of putting a solid and dispersing it or dissolving it in a liquid, can we actually have a liquid initially and go ahead and further disperse and dissolve that in another liquid? And that absolutely can happen. So, flavored oils. Alcohol is another good example where you start with pure alcohol and then you dilute that. So the final amount of alcohol in the solution would be expressed as a percent volume per volume. Okay, and in this case, that would mean the units would be, the top part would be in milliliters of our drug substance dispersed in 100 milliliters of the liquid vehicle. All right. Again, the units for volume are milliliters, and if we're doing a percent volume per volume, then the amount of the drug would be expressed on top in the volume in milliliters of the drug added per 100 milliliters of the vehicle that it was dispersed in. And then lastly is a mixture of solids. in a solid base. So you think, well, how could that happen? Well, what if you just mix two powders? If you mix two powders, then you can express the weight of one of those powders as it relates to the entire mixture. Because remember, when you mix one powder with another powder, the final mixture is the combined weight of both. So you can express the weight of just the one powder as it relates to the total mixture. Or another way to think about this is when we do a cream or an ointment. We call those semisolids because obviously they're not physically hard solids, but they're stiff. They kind of hold their shape a little bit. They're kind of semisolid. And most of our topical creams and ointments have some sort of active drug agent, usually measured by weight, incorporated into this semisolid base. So again, these are very often a situation where the drug is expressed as its percent weight per weight in that cream or in that ointment. And a percent weight per weight, again, just means that you express the amount of drug in there in grams per 100 grams of the solid. Remember, the units of weight will always be grams. So a percent weight per weight would be the grams of your drug per 100 grams of the base or the mixture, the entire piece. Okay, so that was maybe long and drawn out, but hopefully that explains the two. And I just wanted to show you some visual examples of how this is a very common way, this percent expression, whether it's weight per volume, volume per volume, or weight per weight. These are oftentimes the way we label our commercial products, and we're going to have to be able to make calculations and be able to formulate these products, so we have to be able to understand that. So what I show here on the far left is most of your injectables contain drugs that were initially solids that are dissolved into either water or some sort of solution, so that they're dissolved solutions, but there is still a weight of that drug per the volume that it was dispersed in. So, for example, here we have magnesium sulfate injectable expressed as 50% weight per volume. That's how you could calculate how much drug is in each milliliter of that solution. In the middle, as I mentioned before, creams and ointments, topical therapies always have usually some sort of solid drug, active drug that has been dispersed within the base. And so once we measure that active agent by weight, and since we weigh our semi-solid by weight, then we express the activity of that drug as a certain percent weight per weight. In this case, example here, it's beta-methasone valerate, which is a topical corticosteroid for inflammation or a rash, something like that. And it's dosed here as 0.1% weight per weight cream. And the other hallmark for a volume per volume, and these are not as common, but there are some drugs, some essential oils that are dispersed and diluted or are mixed with flavoring agents if it's an oral product. Or another classic example here is alcohol. So this is your rubbing alcohol, 70% ethyl alcohol. What do we mean by 70%? Well, 70 milliliters is actually pure alcohol out of 100 milliliters of this mixture. So we've taken the alcohol and we've diluted it, so that there's what we started with 100% was diluted down to 70%. So only 70% of any volume out of this bottle would contain pure alcohol, the remainder being water. So just another way of how there are almost all commercial products that have some active agent. We usually express the amount of that active agent as some sort of concentration to the whole product. All right, let's just put this into action and do a question here. So this first question will be kind of involving this dilution of a weight per volume solution. So it reads, we have 4 milliliters of Tobramycin ophthalmic solution, which comes commercially available as a 0.3% weight per volume solution. Okay, so we take 4 milliliters of that solution and we dilute it with an additional 2 milliliters of sterile saline solution. By diluting it this way, what is the percentage strength of the final solution? Okay, so where do we start with this? Let's start by first calculating how much drug is in our 4 milliliters. Okay, because the mass of the drug, when we dilute something, the amount of drug doesn't change. However, the volume it finds itself in does change. It expands. So that's why the concentration will go down. Since the mass of the drug isn't going to change, let's figure out how much drug we have in our situation. So let's take the 4 milliliters that we're starting with and multiply it by the percent concentration expressed as 0.3 grams of tobramycin over 100 milliliters. That's the whole point. We said 0.3% weight per volume. The weight is in units of grams. The units of volume are in milliliters. And since it's a percent, it would be over 100 milliliters. So now the units of milliliters cancel when we multiply. So we take 4 times 0.3, divide it by 100, and your final answer would be 0.012 grams of tobramycin. So that's the amount of drug that we have. All right? Well, now what we need to do is express how much drug we would have, okay, when we add an additional not how much drug, but what would the concentration be, when we add an additional 2 milliliters of solution. Therefore, the total drug, the 0.02 grams, is now going to be dispersed in a total volume of the initial 4 plus the additional 2, which would obviously be 6 milliliters, all right? But since this question wants to know what is the percentage strength in the final solution, what we need to know is how much drug would there be if we had 100 milliliters of this concentration. So what I did is let's start with the 100 milliliters we need for the percentage strength, multiply that by the concentration we have in our new situation. And our current concentration now is that we still have our 0.012 grams of tobramycin over the total volume of 6 milliliters, and that comes from our 4 initial plus our 2 additional. So when I take 100 milliliters, my units of milliliters will cancel on the bottom, and I will be units of grams. And so 100 times 0.012 grams divided by 6 gives me a numeric value of 0.2, and the units are in grams. So keep in mind, all I've done is taken the current concentration that I have, which is 0.012 grams over 6 milliliters, multiply that by 100 so that I could see if I had 100 milliliters of that solution, I would have at that concentration, I would have a total weight of 0.2 grams. And that is 0.2 grams for every 100 milliliters. That is essentially an expression as a percent strength, weight per volume. So 0.2 grams over 100 mils is the same as 0.2% weight per volume. And hopefully you can see that. If I told you we had 0.2% weight per volume, you would say, well, that means 0.2 grams per 100 milliliters, since the units of grams or weight per volume is grams per milliliter. So that's how we would answer that question. Now, let's take a variation on that. That question we just completed was about diluting a solution and expressing its concentration. This is a variation where we're going to fortify a solution by adding more drug to it. So not only do we increase volume, but we increase the amount of drug in there. So in this question, it says, we still have our 4 milliliters of this tobramycin ophthalmic solution at the same concentration of 0.3% weight per volume. But now when we add our 2 milliliters, we're not adding 2 milliliters of saline, we're adding 2 milliliters of tobramycin injection. And this injection has a concentration of 80 milligrams per 2 milliliters. All right? It asks, what is the percentage strength in the final solution? So this one, we will start the same way we did the other one, which is to say, okay, well, if I have 4 milliliters of tobramycin ophthalmic solution, how much drug do I have? Take 4 milliliters times the concentration of the tobramycin ophthalmic solution expressed as 0.3 grams over 100 milliliters. Milliliters cancel, and that would give me a numeric value of 0.012 grams. Okay, that's the amount of tobramycin I have from my ophthalmic solution. What's new in this question is the fact that when I add my additional 2 mils, it will actually be providing some additional tobramycin since we're adding the injectable. So let's take the 2 milliliters that I'm going to add, multiply it by its concentration, which we said was 80 milligrams per 2 milliliters. Okay, so clearly the milliliters will cancel and we would have 80 milligrams. But I want to convert my milligrams to grams so that it's in the same units as what we had just done for the ophthalmic solution. So I'm going to then multiply my answer here by the fact that every 1 gram over 1,000 milligrams, so my units of milligrams cancel. So essentially, if I take the 2 times 80 divided by 2 divided by 1,000, my final numeric answer is 0.08 and my units are grams. So again, all we've said at this point is the amount of tobramycin that I'm adding is an additional 0.08 to what was already in the ophthalmic solution. Okay. Now, the last step is identical to what we did before. I want to know the final percentage strength in the final solution, so I'm going to want to know how much drug I would have in 100 milliliters. So I'm going to start with 100 milliliters, and I'm going to multiply it by the concentration, but now the new concentration is the total amount of tobramycin, which is the 0.012 grams from the ophthalmic solution, plus the additional 0.08 grams from the injectable. So that's the total amount of drug now, divided by the total volume, which is still going to be the 4 milliliters that I started with from the ophthalmic solution, plus the 2 milliliters that I'm adding from the injectable. Okay? So when I multiply that across, my units of milliliters cancel, and your final numeric answer would be 1.53, and the units would be grams. So at the concentration we have now, by combining 2 mils of the injectable with the 4 mils of the ophthalmic solution, we would have a total of 1.53 grams for every 100 milliliters. Okay? Well, since that's per 100 milliliters, that's the same as 1.53% weight per volume. Because by definition, 1.53% weight per volume would have 1.53 grams of tobramycin for every 100 milliliters. And that is essentially the concentration we have created. And that's the answer to this question, and hopefully you can see the big difference was from the one we did before is that by adding the injectable versus just saline, while we still increased the volume, that is, we diluted the 4 mils up to 6 mils, in this case, we added additional drug, and so we had to account for the additional mass of the drug in the numerator of this equation. So hopefully that makes sense. All right, let's move on to the next question, which is now switching from weight to volume to talking a little bit about volume per volume. All right, and the question reads, how many liters of a mouthwash can be prepared from 150 milliliters of cinnamon flavor if its final concentration of the mouthwash, in this case, is to be 0.4% volume per volume? And so this is kind of an example. You look over here on this ACT product. This is a mouthwash that's been flavored with some cinnamon. Okay, where did the cinnamon come from? Well, they used this kind of high concentration cinnamon flavoring and then diluted it into this final mouthwash, and that's exactly what we're doing here. But the question is saying, okay, if I'm starting with 150 milliliters of this concentrated cinnamon flavor, how much of this ACT mouthwash, if you will, can I make from that much flavoring if the flavoring has a concentration in the final mouthwash of 0.4% volume per volume? Okay, so where do we start with this? Well, let's start with the volume of the cinnamon flavor that we have. So if I have 150 milliliters of this cinnamon flavoring, what I'm going to want to do is convert from the cinnamon flavoring volume that I know to the volume of mouthwash that I could produce. So I'm going to take my 150 mils of cinnamon, multiplied by the concentration we were given, but expressed as 100 milliliters of mouthwash on top per every 0.4 milliliters of cinnamon flavoring. Okay? Because what does 0.4% mean? It means 0.4 milliliters of the cinnamon for every 100 milliliters of mouthwash. That's by definition what percent volume per volume is. In this formula, though, notice we've set it up so that our units cancel correctly. So again, I'm going to multiply my 150 mils of cinnamon by the 100 mils of mouthwash on top over the 0.4 milliliters of the cinnamon. That way, units of milliliters of cinnamon cancel, and I'm in units of milliliters of mouthwash. We're basically done, but the question did ask for the volume to be expressed in liters. So let's convert our milliliters to liters by multiplying it by, there's 1 liter for every 1,000 milliliters. Therefore, milliliters cancel, and my final answer, if I do the math from left to right, my final answer would be 37.5, and my units would be liters, and that is liters of mouthwash. So basically, from 150 mils of cinnamon flavor, I could produce 37.5 liters of mouthwash. That's going to be a lot of clean mouths, so that's a good thing, I guess. All right. Well, I'll remind you, so far we've completed a question for Tobramycin that involved a percent weight per volume. Our mouthwash question involved a percent volume per volume. And so now this question involves a problem that it will be a percent weight per weight example. So the question reads, you need to prepare 120 grams of an ointment containing 0.02% weight per weight of triamcinolone acetonitrile. And that's usually abbreviated as TAC, T-A-C. You have available a triamcinolone or TAC injection that contains 40 milligrams per mil. How many milliliters of this injection will you need to compound the ointment? All right, so again, this is confusing in the sense that there's a lot of numbers. There's 120 grams, 0.02%, 40 milligrams per milliliter. Where do you start? Well, you start by, what am I trying to prepare? In the end, I have to have enough drug for my 120 grams of ointment. So let's start with 120 grams of ointment. Let's figure out how much triamcinolone I need to make that ointment at the percent that I need. So if I start with 120 grams, and let's multiply it by its concentration, expressed as 0.02 grams of triamcinolone for every 100 grams of ointment, because that's the key to this question. That's how you would interpret a 0.02% weight per weight concentration would mean 0.02 grams of drug, in this case triamcinolone, per 100 grams of ointment. This way the units of grams of ointment cancel, and I will be in grams of triamcinolone. Now, I'm eventually going to get to my injectable here, but my injectable concentration of triamcinolone is in milligrams. So my next step will be to convert my grams of triamcinolone to milligrams by multiplying by the fact that there's 1,000 milligrams for every 1 gram. Now units of grams cancel, and I'm on units of milligrams. Lastly, what I need to do is convert my milligrams of triamcinolone into the volume of the injectable that I need. So let's multiply it by the concentration of the injectable, expressed as per every 1 milliliter on top, there is 40 milligrams of triamcinolone. And triamcinolone, or the 40 milligrams, is on the bottom, so that my units of milligrams cancel. And when I do all the math from left to right and cancel all my units, the only remaining units would be milliliters. And the numeric value you should get is 0.6. So essentially, I need 0.6 milliliters of this injectable to provide the total amount of triamcinolone I need to make 120 grams of an ointment have a concentration of 0.02% weight per weight, or 0.02 grams for every 100 grams of that ointment. And that's essentially the 0.6 milliliters is the answer to this question. Now, this question is interesting because it has to deal with when mixing solids with solids, all right? The fact that, and when we talk about a percent weight per weight, when we make or compound these products, the issue is we have to keep in mind is that the weights are additive. So when we add 100 milligrams of one product to 100 milligrams of the other and mix them together, the final weight is 200 milligrams. The weights of the individual ingredients are additive. And that can be somewhat problematic sometimes in our formulations. So and you'll see that in this example. So let's read the question. It says, how many grams of tannic acid must be added to 320 milliliters of glycerin having a specific gravity of 1.25 to make a 1% solution, but the concentration of 1% is expressed as a weight per weight. So even though this is in the end going to take a solid and mix it with a liquid and have a solution at the end, the concentration we are expressing of our drug here, this 1%, is a weight per weight, not a weight per volume. And that's kind of a key difference here in this question. So actually, even though we were given, so where do we start with this? Well, since our concentrations are expressed as weight per weight, we need to convert this volume of glycerin into a weight and now do all of our calculations essentially in weight, meaning grams. So the first step on this question would be, okay, so I'm told 320 milliliters of glycerin, but I'm also given the specific gravity, and I'll remind you, specific gravity in this course will be treated like density for reasons we've talked about. we're going to go ahead and convert the volume of this glycerin to its corresponding weight. We would do that by taking 320 milliliters of glycerin, multiply it by its density / specific gravity, which means 1.25 grams of glycerin per milliliter. That way the units of milliliter cancel. So 320 times 1.25 would be 400 grams of glycerin. So now we know how much glycerin we are going to be combining with our tannic acid. The problem is we don't know how much tannic acid. So what's important here going forward, and this is going to be kind of a little mind reading here. Let's start on the left-hand side. What we do not know is the amount of tannic acid to add, okay? But we do, so we're going to set that equal to X. X equals the weight in grams of the tannic acid, all right? So let's set up a proportion, because a percent weight per weight, essentially, is the amount of our drug per 100 grams. And we know that. We want a 1% weight per weight. So look on the far right on this equation here. This is much more straightforward. What I'm setting here, my proportion, is 1% weight per weight, means 1 gram of tannic acid for every 100 grams of mixture. Hopefully you can see that on the far right. 1% weight per weight means 1 gram of tannic acid for every 100 grams of mixture. Okay? So that's what we want to make. So let's set that equal to, how are we going to make it? Well, we don't know how much tannic acid we're going to add. We said that's equal to X. So that's why on top, we know that we're going to have X grams of tannic acid. Set that over, well, what is the mixture? We actually do know something about the weight of the mixture. The weight of the mixture is going to be the combination of the weight of the tannic acid plus the weight of the glycerin. There isn't anything else in the mixture. So we know, while we don't know exactly what the tannic acid weight is, we know it's X. We set it equal to X. So would you agree that the total weight of this mixture will be the X grams of tannic acid plus the 400 grams of the glycerin? So we're going to set the denominator here equal to X plus 400, and that's essentially in the units of grams per mix. All right? Guess what? We now have an algebra problem with just one variable, which is X. So let's solve for X. And when we solve here, do not carry the units. So the first thing I always like to do with these questions is set up the formula here. Make sure that we have the units are set the same. So let's look on top here. My X represents grams of tannic acid, because on the right-hand side of the equals, we have grams of tannic acid. On the bottom, we're in grams of mixture, and on the right, we're in grams of mixture. So my units are set up correctly, and I know what my units are. So as I do my algebra here, drop the units, or they'll just mess you up. So just leave off the units. So essentially, if we cross multiply to solve this algebra, we'd have the X times the 100. So on the left-hand side, I have 100X. Set that equal to X plus 400 times 1. That's easy. That's just X plus 400. So now you can see I have 100X equal X plus 400. So let's subtract X from both sides to get rid of the X on the right. So if I subtract an X, that means on the left I have 99X equal to just 400. If I divide each side by 99, I will just get X. So X would equal 400 divided by 99, which is 4.04. Now I can go back and remember, what were the units I assigned to my X value? It was grams of tannic acid. So my 4.04 represents 4.04 grams of tannic acid. And that's essentially the answer to this question. And wanted to know how many grams of tannic acid. So if we add 4.04 grams of tannic acid to 400 grams of glycerin, we would make this mixture, and the final concentration of tannic acid in this mixture would be 1% weight per weight. Okay, just because that's a little confusing, and let's just see if you can do it again, I guess. Let's answer the same question now. It is exactly the same. How many grams of tannic acid must be added to 320 milliliters of glycerin, having a specific gravity of 1.5, now to make a 20% weight per weight solution? So the only thing difference here is the concentration. It'll make our math a little more complicated, maybe for some of you in the algebra. You'll see here in a minute. But essentially, let's work it the same way. So can you see? I'll go through this a little more quickly and see if you can keep up. We'd start with the same thing. Since our final concentration is in weight per weight, let's change the volume of glycerin to its weight. do it the same way. 320 milliliters of glycerin times its density is 1.25 grams per milliliter. Units of milliliters cancel. I have 400 grams of glycerin. All right. I'm still going to set X equal to the weight of tannic acid in grams, since I don't know what that weight is. Now, looking at the far right, what's different here is that we were told we have a 20% weight per weight solution. So on top would be 20 grams of tannic acid for every 100 grams of mix. I'd set that equal to, again, X on top, since X represents the weight in grams of tannic acid. And the denominator is still the same. My final mixture will be that weight of whatever tannic acid that is, plus the 400 grams of glycerin. Okay? So now when we cross multiply, we still have X times 100, or 100X on the left. What's different now is you've got to multiply 20 into the combination of the X plus 400. So 20 times X would be 20X, plus 20 times 400 gives you 8,000. So there's the 100X equals 20X plus 8,000. So hopefully you got that. It's a little bit of the difference here. We solve it the same way. Let's subtract 20X from both sides. That would leave me 80X on the left equal to just 8,000. 8,000 divided by 80 is 100. So essentially we need 100 grams of tannic acid to be able to produce so when we have our 100 grams of tannic acid and we add it to our 400 grams of glycerin, we would have 100 grams of tannic acid over 500 grams total mixture, and that essentially reduces down to 20%, which is 20 grams of tannic acid for every 100 grams of mixture. That's a 20% weight per weight concentration. All right, let's switch gears here a little bit. We've been talking a lot about percentages. We can express drugs as a percent weight per volume, volume per volume, and lastly here has been weight per weight. So let's do something different. It's a variation. It's all the same, but it's expressed in different ways. So in some situations, you will see a concentration expressed in parts per million, ppm. Now clearly, million is a big number, but when we have very, very dilute solutions, that is, the concentration of our drug is very, very low, then it isn't very useful to express it as a 0.00003%. That's weird. And it's subject for errors because of all those zeros. So instead, we can just express it as parts per million. However, I'll just say, the parts per million is the relation of the part to the whole, the solute to the solution, if you will, but that it could still be a weight per weight, or it could be a volume per volume, okay? So, or it can still also be a weight per volume. It can be still any combinations of those, okay? And lastly, I will just mention, we won't give examples of this, but especially when you're looking at gases or maybe contamination in the air, you can also express things in parts per billion, or ppb. You'll see that sometimes as well. Again, not so much in medicine, but it can be done in environmental sciences. All right, let's just put this into action. The question is, if a commercially available insulin preparation contains 1 ppm, or parts per million, of proinsulin, how many micrograms of proinsulin would be contained in a 10 milliliter vial? Okay, so think of this proinsulin as kind of a contamination that, it won't work in the body, so having it in there doesn't do us any good. So we want to minimize that. So if there's always a little bit of it, well, that is 1 parts per million that occurs in our manufacturing process, how much of that would be in a 10 ml vial? We don't want that much contamination. So how many micrograms of this contamination, proinsulin, if you will, is in our insulin vial? Well, where do we start here? Let's start with what we have solid, which is, 10 milliliters. That is what we know firm, is that we're trying to determine how much contamination is in this 10 milliliter vial. So let's start with the 10 milliliters. So we have 10 milliliters of insulin. Let's multiply it by its concentration of the proinsulin, which we said was 1 ppm. 1 part per million means 1 for every 1 million. Since in this case, we are talking about a proinsulin, which is a solid, in a volume of insulin, so it's going to be in the units of grams per milliliter. This is a weight per volume, okay? And that's because our insulin is expressed as a volume, 10 milliliters, and the amount of that we have is expressed in the weight of the proinsulin. So let's multiply 10 milliliters times the fact that would be 1 gram of proinsulin for every 1 million milliliters of insulin. Okay? So in the units of grams per milliliter are the units of weight per volume. So if we multiply that across, my units of milliliters of insulin will cancel and will be in grams of proinsulin. So the last step wants to know the micrograms of proinsulin. So what we need to do is convert from grams to micrograms. And you certainly can do that in one step. My mind is so small, I like to do it in small steps. So I'm going to convert 1 gram of proinsulin to milligrams because I know there's 1,000 milligrams for every 1 gram. So my grams cancel. Now I'm in milligrams. I also can remember that there's 1,000 micrograms for every 1 milligram. So I'm going to multiply it again by 1,000 micrograms per milligram. Units of milligrams cancel. And essentially, my final units would be in microgram. Well, if you can kind of see already that 1,000 times 1,000 is 1,000,000 in terms of the numerator, then you can see that the denominator has 1,000,000. Those will cancel. And again, if you just do the math from left to right, you can see that your final numeric answer would be 10. And 10 would be 10 micrograms of the proinsulin. So that's how you could calculate that. And it's just using this kind of different way to express the concentration in parts per million. But hopefully you understand. It still doesn't change the components. In 1 part per million, and if it's a weight per volume, then the units are grams per milliliter. It's just 1 gram per 1 million milliliters. It's just a large number, but it makes an easier way of expressing the concentration instead of trying to express it as a very, very small percent concentration. All right. Another way to express concentration that has historically been confusing for students is ratio strength. And it's really where you just say you have a concentration of 1 to 1,000 or 1 to 200, 1 to 500. The 2 is written as a colon. But it's still the relationship of a thing to the whole. And it can be a solid in a liquid, it can be a liquid in a liquid, or it can be a solid in a solid. So it's the same thing as what we've discussed for percents, weight per volume, volume per volume, or weight per weight. It's just not using it per 100. Remember, percents standardize everything per 100 mils or per 100 grams. Ratio strength doesn't standardize it. It gives you simply the relationship of 1 to the whole. And so that's why you'll see it as 1 to something. All right? So anyways, let's just read the question. Hopefully we'll apply it and it will make more sense. So it says, the dose of a drug is 2.5 milligrams and is supplied as a solution with a concentration of 1 to 200. And we're given that as a concentration in weight per volume. So the concentration of 1 to 200 weight per volume. This solution is administered using a dropper with a drop factor of 12 drops per milliliter. How many drops would be needed to supply this dose? So let's start with the fact that, what is the dose we're trying to give? 2.5 milligrams. So let's start with the 2.5 milligrams, and now let's multiply that first to convert its units from milligrams to grams. So we do that by multiplying by the fact that in every 1 gram, there's 1,000 milligrams. So milligrams cancel, and we're in grams. Why did I want my dose in grams? Because remember we said concentrations are standardized. So when I say weight per volume, the weight will have the units of grams and the volume per milliliter. So we need to be in grams. What does a concentration of 1 to 200 mean? If it's weight per volume, it means 1 gram for every 200 milliliters. Remember, we're not a percent, so the whole 100 doesn't apply here. Ratio strengths are not percents. It's simply the amount of the part, the solute, per the total amount of the mixture or solution. And you can express that now in any volume since we're not in percents. In this case, since it's weight per volume, that means 1 gram per 200 milliliters. So getting back to this question, since I have my dose in grams, I want to multiply it by the concentration expressed as 200 milliliters on top has every 1 gram on the bottom. And that way the units of grams cancel, and I now have my volume of this solution that would provide my 2.5 milligrams. However, we're not done because it wanted us to express that volume in terms of the number of drops using our set. So the last step is to multiply the fact that we know we get 12 drops for every 1 milliliter. By putting milliliters in the bottom, the units cancel. If I do my math from left to right, my final number would be 6, and my only remaining units would be drops. So the answer is 6 drops. 6 drops of this solution, which is 1 to 200 concentration, would provide 2.5 milligrams of my drug. And hopefully you see where that comes from. And this expression of the ratio strength is done the same way regardless of whether it's weight per volume, volume per volume, or weight per weight. It's still going to be 1 milliliter per whatever number of milliliters, or 1 gram per whatever number of grams. So again, it's just not standardized per 100 when it's not a percent. All right. Well, let's end this lecture with a series of questions related to this same prescription scenario. So it says, a formula for metronidazole 1% topical gel is as follows. And you can read the prescription there. I won't go through the individual ingredients. There's several of them. We'll refer to them here in a minute. But clearly we have metronidazole, 1 gram, with some additional formulation agents. And again, the parabens, methylparaben, propylparaben, those are preservatives to help prevent contamination in our product. Propylene glycol is kind of a stabilizer. It helps disperse the metronidazole. Ooh, it's got hydrochloric acid in it. That seems weird. Well, sometimes we need to do that as essentially an acidifier. It's not a lot, and keep in mind, the total formula here will produce 100 milliliters of gel, so it's a relatively small amount, and the only reason we're adding it is to act as an acidifier to adjust the stability of our drug. So some drugs are basic, and we need to kind of acidify the final product so that it doesn't create any problems on the skin. So anyways, they're formulation ingredients. All right. So let's get to the first question. The first part, letter A here, says that concentrated hydrochloric acid is 37.25% weight per weight. Okay. And has a specific gravity of 1.18. How many milliliters of this concentrated acid would you need to prepare 30 milliliters of the 10% weight per volume solution that we need to use to prepare this formula? Okay, so let's look back above. Remember how I talked about the hydrochloric acid used as kind of an acidifier to lower the pH? What we're using in our formulation is a 10% weight per volume solution. Okay, well, we need to make that. That doesn't come commercially available. What we're saying is that what comes commercially available is a much more concentrated 37.25% weight per weight concentration solution. So how much of that do I need to make 30 milliliters of the solution I would then use in my formula? Okay, so there's a lot going on there, but the important thing here to realize is this is an interesting question where we're mixing weight per volume concentrations with weight per weight concentrations. All right, so let's start with getting how much do we need? How much hydrochloric acid do we need? Well, we need enough to make 30 milliliters of my 10% solution. So let's start with 30 mils. I'm going to take my 30 milliliters, multiply it by the concentration of that I'm trying to make, which is 10% weight per volume. So if I take 30 mils times 10 grams per 100 milliliters, which is 10% weight per volume. If I multiply that way, can you see that my units of milliliters cancel, and what I'm determining is the grams of hydrochloric acid I need to make my 30 mils. All right. Where am I going to get that weight of hydrochloric acid? I'm going to get that weight by using the concentrated hydrochloric acid, which comes as 37.25% weight per weight. But this is the trick. Now, when I set up this multiplication, remember, my 10 grams on top there was the grams of the hydrochloric acid pure I needed. So I'm going to multiply that by 100 grams of the concentrated mixture over the 37.25 grams of pure hydrochloric acid, because that's what's in 37.25% weight per weight would be 37.25 grams of hydrochloric acid in 100 grams of mixture. Okay, since what I first solved for was the amount of hydrochloric acid I needed, I then multiply it by the 100 grams of mixture over the 37.25 grams of hydrochloric acid. So now my units cancel, and I'm in grams of my mixture, okay, my concentrated mixture. I was told that the specific gravity or density of that mixture was 1.18. So my last step is to multiply by the fact that every 1 milliliter of this mixture weighs 1.18 grams. And I do that so that my units of grams cancel, and I'm now in volume. So if I do all that math from left to right and go all the way across, I realize I need 6.8 milliliters of this concentrated hydrochloric acid solution to provide the right amount of hydrochloric acid that when I dilute it to 30 milliliters, I would essentially have a final resulting concentration of a 10% weight per volume that I could use then to formulate my gel. All right. So let's finish off on kind of the hydrochloric acid idea here, because it says what is the final percent strength, weight per volume of hydrochloric acid in this actual formula. So in knowing that we're going to be using a 10% weight per volume solution and 1.5 milliliters of that solution, what is my final concentration of hydrochloric acid in this formula? And again, do you think it wants to be high? No, we don't want a high amount of hydrochloric acid in our gel. So let's figure out what is our final actual percent strength and weight per volume of this gel. Okay, of hydrochloric acid in the gel. So, where do we start? Well, let's start with the fact that what's being put into the gel is 1.5 milliliters of our hydrochloric acid solution. So I set that on top. But I went ahead and I'm going to leave it, but I wanted you to keep this proportion in mind. That's the volume of hydrochloric acid that's in 100 milliliters of my gel. Because if you look at the formulation down at the very bottom, we're adding enough purified water, QSAD, which means up to a total of 100 milliliters. So, would you agree? We have 1.5 milliliters of our hydrochloric acid in 100 milliliters of gel. Now, don't mess with 100 mils of gel. Let's just go ahead and convert this volume of hydrochloric acid, because that's going to be a volume per volume. We want it a final weight per volume. So let's multiply this by the fact that the 1.5 mils of hydrochloric acid that I'm adding has a concentration of 10% weight per volume. That means 10 grams per 100 mils of the liquid. My units of milliliters cancel, and I now have grams of hydrochloric acid. So if I do that math without dividing the 100 mils of gel, so 1.5 times 10 divided by 100 gives me, on the numerator, 0.15 grams. And again, I said in the beginning, that's standardized. That's the amount per 100 mils of gel. So 0.15 grams per 100 mils of gel means we have a 0.15% weight per volume concentration, and that's our final answer. So by adding 1.5 mils of this hydrochloric acid, we're actually adding 0.15 grams based off of its concentration, and that 0.15 grams is going to exist in a total gel volume of 100 mils. So 0.15 per 100 mils is 0.15% weight per volume. All right. So let's move on, and remember we can express concentration not only by weight, but also by the number of molecules. And this is what question C says. It says, what is the molar strength of hydrochloric acid in this formula? Well, we just won't let go of this hydrochloric acid. We've expressed it now. We just said it's 0.15% weight per volume. Well, now instead of saying weight, let's express it in molar strength. Okay, molars being the number of moles per liter. So that's an important thing to keep in mind. I'll show you my work here in a minute. But molar, M-O-L-A-R, stands for the number of moles standardized per a volume of a liter. Moles per liter is the final units we're trying to express our hydrochloric acid in. All right, so let's go back here and look at where I start. I start the same place I did in the previous question. We have 1.5 milliliters of hydrochloric acid in 100 milliliters of gel. All right. So where do we go from here? Let's do the same conversion we did before, where we're going to say, well, with 1.5 mils of hydrochloric acid times its concentration, which was 10 grams of hydrochloric acid per 100 mils of hydrochloric acid. My units of mils of hydrochloric acid cancel. I'm now in grams of hydrochloric acid. The trick here is now to convert grams to moles. How do we do that? We do it because we know the fact that 1 mole of anything is equal to its formula weight in grams. That's by definition. Okay, a mole is equal to the formula weight in grams. So we can now multiply this by the fact that we could say we have 1 mole on top over the formula weight of hydrochloric acid in grams, and we were given that as 36.46. So now when I multiply that amount out, my units of grams of hydrochloride cancel, and I would be in moles of hydrochloride. Okay, again, without dividing out the volume yet, if you just do the 1.5 times 10 divided by 100 divided by 36.46, that number would be 0.0041 moles. Okay, and that's still per 100 mils of gel. The reason that that's important is it wanted the molar strength, was not moles per 100 mils, but moles per liter, which would be moles per 1,000 mils. So what I'm doing now to get to my final answer, I need to multiply both the top and the bottom by 10. So if I multiply the top of the numerator by 10, I get 0.041 moles, and on the bottom I'd have 1,000 milliliters. The reason I did that is 1,000 milliliters is the same as liters, so essentially my final answer is 0.041 molar, because that would be 0.041 moles per 1,000 milliliters, which is what we've converted to. And that is the answer to this question and the end of this lecture. So hopefully you found this helpful. It was just a variety of different questions that make you convert to get to the final answer. You have to somewhere in there use a concentration, and that concentration certainly can be expressed in many different ways depending on the type of the relationship of whether it's a solid to a liquid to a liquid, or a solid to a solid. But in the end, the way that you use those numbers are just needs to be consistent. So hopefully this was helpful.